So now let's talk about the difficulties that we have with parallel programs and parallel processors in general. So we saw previously that we had some serial code in the example we were looking at. And so how much does this little tiny, almost insignificant non-parallel part hurt us? Well, where did it come from? So here's the example where we're going to count the words in parallel. We decided the first thing we'd have to do is guess where it's split and then walk back until we found a space. And then once we found the space, we could divide up the work. So once we divide up the work, we can do the counting in parallel. But to divide up the work, we have to do this first finding the middle part in serial. So not all of our program can be parallelized. The part here where we find the stuff in the middle, that has to happen in serial. We can't have two processors doing that very easily. But counting the words, we can then easily do in parallel once we've done that. So how much does this hurt us? Well, let's take a look at an example. Say I have a program that's 75% parallel. That is 75% of the program time we can run on multiple processors, and 25% serial. That is 25% of it we can't split up and run on multiple processors. So I have 100,000 processors to run on. How much faster is my program? Well, here's a picture of the program. 75% of it is parallelizable, so this part can run faster on more processors, but this 25% can't run any faster. It's serial, we can't parallelize it. So when we parallelize the program, this 25% is still going to take the same amount of time. But this 75% is going to go 100,000 times faster because I have 100,000 processors. So that's going to go really a lot faster. In fact, what we're going to see is that 75% goes 100,000 times faster, so that's nearly infinitely faster. So this 75% of it is now going to take almost zero time. So what are we left over with? Well, we're left over with that 25% that's serial that doesn't go any faster. So our final speed? Well, 75% of our program goes infinitely faster, or 100,000 times faster. So 75% goes down to 0% of the time, but that 25% stays around. So overall, my new parallel program takes 25% of the time of my previous one, so it's 4 times faster. So I used 100,000 processors, but because only 75% of my program could be parallelized, I'm only going 4 times faster, despite using 100,000 processors. So if 90% of a program can run in parallel, and I have 100,000 processors, how much faster can my program go? Well, it can go 10 times faster. So just like the picture we have up here, 90% of the program will now go infinitely faster, so I'll be left over with 10%, and 10% left is 1/10 of the program, so it ran 10 times faster. So it's kind of disappointing that I had a program that 90% of it could run in parallel, and I had 100,000 processors, but I'm only running 10 times faster. So this is called Amdahl's law, and it basically says that the parallel performance is limited by the serial part of your code. And here's the equation, and you should pay attention to this equation because you're going to need to use it. So p is the parallel fraction. So here 1 minus p, this is the serial fraction. S over here is the speed up. This is how much you speed up the parallel fraction. So if I'm going to run a program 10,000 times faster, this would be 10,000, and if 90% of it is parallel, this would be 0.9. So let's take a look at an example. So p equals 75%. 75% of my program is parallelizable, and the speed up for that is going to be 100,000, just the example we had before. So now I've got 1 over 25%, or 1 minus the parallel percent, plus the parallel percent, 75, over 100,000. And what you get is basically 1 over 25, because this 75% over 100,000, this part in here basically goes away, it goes to 0. So it's going to be 4 times faster. Now we can plot the potential speed up of Amdahl's law for different degrees of parallelism. So here, if your program is 75% parallel, you can see the maximum speed up you get is 4 times. Even with 1,024 processors, you're only running 4 times faster. If I have 4 processors, I'm running less than 4 times fast. Here's a program that's 90% parallel. So with 90% parallel and 1,000 processors, I'm only 10 times faster. Here's a program that's 99% parallel. So if I have a program that's 99% parallel, that means only 1% of the program has to be done sequentially. With 1,000 processors, the best I can do is 91 times faster. So this is a little disappointing. It says that if we have any of our program that's serial, it's going to really hurt our ability to run faster with parallel processors. And if you look at an example here, say Intel's trying to sell you an 8-core processor. So if you have a program that's 99% parallel, you might get up doing pretty well with an 8-core processor. But if your program's only 90% parallel, an 8-core processor is only going to run 5 times faster. It's not going to really help you that much. So let's look at another problem with multi-core processors, and that's resource sharing. So we know that how much cache you get affects how fast you run. And we know these processors have large on-chip caches. So here's a picture of a multi-core processor, and you see we've got all these cores here, and then we've got this large cache that they're all sharing. And this is shared between all of the cores, so it's going to depend on, so how much cache you get is going to depend on what the other cores are doing. So here's the way it looks. We have each of these cores, they have their little teeny private caches, they get all to themselves, and then we have this big cache that they share. And if we want to run just one program, that one program is going to get all of its private caches plus all of the big shared cache. But if we run 2 programs, each of the programs gets their private cache, but now they share this big shared cache. So maybe the blue program gets most of the cache and the red program only gets a little bit, or maybe it's the other way around, with the blue program getting a little bit and the red program getting a lot. The problem here is that performance depends on how much cache you get. So here's a graph. It shows that as this application, depending on how much cache it gets, its performance gets slower. So as it gets less cache, the performance gets worse. And so you can see up here that if this program is the blue program and I give it less cache, it's going to run more slowly. So this resource sharing is a problem. Let's take a look at that here. Here I've got 4 programs that I'm going to run on a multi-core processor. And when I run them alone, they get this throughput, or this performance. When I run them together, their performance gets hurt. So you can see these 3 applications run noticeably slower. This application runs only a teeny bit slower. But overall, we have 30 to 40% slowdown due to sharing the cache. So this is another problem with multi-core processors. We share the cache on the chip, which makes it hard to know what our performance is going to be. So let's take a look at some extreme multi-core or many-core processors. So here's NVIDIA's Kepler GPU, has 1500 processor cores, and here's Intel Xeon Phi, it has 62 processor cores. Now you look at that and say, that's great, it's got to run really fast, but remember what Amdahl's law says. If our program is 75% parallel, the best we'll do is 4 times faster. If it's 90% parallel, the best we'll do is 10 times faster. Even if our program is 99% faster, the best we're going to do is 91 times faster. So you've got 1500 cores here, but your program needs to be more than 99% parallel to get more than 100 times speed up. So this is a really limiting factor. And this is why we typically see lower speed ups on GPUs than we expect. So to summarize things here, transistors got smaller, but we can't reduce the voltage. So as a result, we can't increase the clock frequency. So what are people going to do? Well, we move to multi-core. The idea is I'll sell you 4 cores, and of course 4 cores is faster than just having 1 core. But we saw some problems with this. It's hard to write parallel programs. We need to deal with synchronization and load balancing. We saw how Amdahl's law limits the improvement. So even if we're 99% parallel, we can't go any more than 100 times faster. We also saw the issue of shared resources. If you're running multiple programs together and they're sharing a cache, it's hard to understand the performance. And the fundamental problem here is that programmability is inefficient. That is, we built processors that are easy to program, but it means they're spending most of their time doing things other than work. Remember all the stuff that we had in the pipeline that wasn't the ALU. The ALU is the only part of the pipeline that's actually doing the additions and subtractions in the programs. Everything else is doing other stuff, and that's why they use so much power. So we're paying a lot of power to make our processors easy to use, and that's why we have this problem with power. So a question about cache sharing. Could cache sharing in a multi-core processor ever make the program go faster? The answer here is yes, it can. If one of the program brings data into the cache that the other program is going to use later, then the second program doesn't have to wait for it because it's already in the cache. This is called prefetching. And if you prefetch data, it'll speed up the program. In fact, prefetching works so well that processors today all have special hardware to try and guess what data the program is going to need and go get it ahead of time. If a 99.9% parallelizable program is run on a Kepler processor, what's the best performance you can get? So 99.9% can be parallelized. We've got 1,536 cores. Well, it's going to be 606, and that's just applying Amdahl's law. So Amdahl's law gives us 1 over 1 minus 99.9% plus 99.9% over 1,536, which is 606 times speed up. The best we could possibly do is 1,000 times if we sped up that 99.9% infinitely. So even with 1,536 cores and a program that's only 0.1% serial, we get less than half the speed up that the number of cores would suggest. So again, not very encouraging. And this is exactly why we see such low speed ups on GPUs. GPUs say we've got 1,500 cores, but typically only get between 2 and 5 times speed up because so much of your program is serial.